It's everywhere. So, what is electricity really? Think about it. It's a form of energy. It's all around us all the time. At its very smallest level, everything is made of tiny things called atoms. Inside these atoms are even tinier particles. Some of these particles have a special property called an electric charge. We call these particles electrons. When these little electrons start to move or flow from one atom to another, that's it. That's electricity. It's the flow of energy, a powerful force that we have learned to use in so many amazing ways. It's not magic, it's science. You've definitely seen electricity in action, even if you didn't think about it. Have you ever seen a big, flashy lightning storm? That's electricity. It's a huge, powerful spark of static electricity built up in the clouds. The clouds build up so much charge that it needs to go somewhere, so it zaps down to the ground. That's a giant natural display of electrical power. It's the same kind of energy that makes your hair stand up if you rub a balloon on it. That little spark you feel when you touch a doorknob on a dry day. That's also static electricity, a tiny version of a lightning bolt. Electricity isn't just something that happens during a storm, though. It's happening inside our own bodies right now. Your brain uses tiny electrical signals to send messages to the rest of your body. When you decide to wiggle your toes, an electrical signal travels from your brain, down your nerves, all the way to your feet. It tells your toe muscles to move. It's how we think, how we move, and how we feel. Even some animals, like electric eels, have mastered using electricity to defend themselves or find food. Electricity is a fundamental force of nature, an essential part of the universe. So, you see, electricity isn't something people invented. It was always here. It's a natural phenomenon that has existed as long as the universe has. For thousands of years, people saw lightning and felt static shocks, but they didn't understand what it was. They thought it was mysterious or magical. But then, curious people, scientists, started to ask questions. They started to experiment and observe, slowly piecing together the puzzle of this invisible force. We didn't create electricity, we discovered its secrets and learned how to harness its incredible power. Our journey to understand electricity took a long time and involved many brilliant minds. It wasn't one person who suddenly discovered everything. Way back in ancient Greece, people noticed that if you rubbed amber, which is fossilized tree sap, with fur, it would attract little things like feathers. They were observing static electricity, but it wasn't until much later that people started to really study it. One of the most famous early experimenters was Benjamin Franklin. In the 1700s, he did his famous and very dangerous kite experiment during a thunderstorm to show that lightning was, in fact, electricity. This was a huge step forward. As we moved into the 1800s, things really started to heat up, electrically speaking. Scientists like Alessandro Volta created the very first battery. He found a way to create a steady, continuous flow of electricity, which was a game changer. This allowed other scientists to do all sorts of new experiments. Then came Michael Faraday, a true science hero. He made one of the most important discoveries of all. He figured out that you could use magnets to create electricity. This principle, called electromagnetic induction, is the basis for the electric generators we still use today to make almost all of our power. Of course, we have to talk about Thomas Edison and Nikola Tesla. These two were pioneers who helped bring electricity into our homes. Edison is famous for his work on a practical, long-lasting incandescent light bulb. He wanted to create a whole system to deliver electricity to cities so everyone could have light. Nikola Tesla, on the other hand, was a genius who championed a different kind of electrical system called alternating current, or AC. AC could travel over much longer distances than Edison's direct current, which made it more efficient for powering entire countries. The debate between them was called the War of the Currents, but in the end, Tesla's AC system became the standard for power grids around the world. So, while Edison helped create the demand for electric light, it was Tesla's vision for distributing power that truly electrified the planet. It's important to remember that all these people, from the ancient Greeks to Franklin, Volta, Faraday, Edison, and Tesla, built on each other's work. Science is a team sport played over centuries, with each generation adding a new piece to the puzzle of understanding our world. Section 3. How does it all work? The electric flow. Let's break down how electricity works in a way that's easy to understand. Imagine electricity is like water flowing through a garden hose. The water itself is like the electrons, the tiny charged particles. The hose is like a wire, which is a path for the electrons to travel along. Wires are usually made of metals like copper because electrons can move through them very easily. We call materials that let electricity pass through them conductors. The water pressure in our hose is like voltage. Voltage is the push or force that makes the electrons start moving in the first place. Now, the amount of water flowing through the hose at any moment is like the current. In electricity, current is the measure of how many electrons are flowing past a certain point each second. The more electrons that are moving, the higher the current. To get anything done with electricity, you need both voltage, which is the push, and current, which is the flow. You also have something called resistance, which is like a squeeze or a kink in the hose. Resistance slows down the flow of electrons. Things like the filament in an old light bulb have high resistance, which causes them to heat up and glow. To make all of this happen, you need a complete path, which we call a circuit. A circuit is like a racetrack for electrons. It has to be a closed loop that starts at a power source, like a battery or a power plant, goes through the wire, powers a device, like your phone or a lamp, and then travels back to the power source. If there's a break anywhere in the circuit, like when you flip a light switch to the off position, the path is broken. The electrons stop flowing, and the device turns off. That switch is simply a gate that opens and closes the circuit. So when you plug something into a wall outlet, you are completing a circuit. The outlet is connected by a massive network of wires to a power plant. The power plant uses a generator, which works using Michael Faraday's discovery about magnets and wires, to get electrons moving. Those moving electrons travel through huge transmission lines, then to smaller lines in your neighborhood and finally right into your home. They flow through the cord, power your device, and flow back out, completing a giant circuit that stretches for miles and miles. It's a simple idea, but on a massive scale. Section 4. Powering our world and our future. Think about your day. You probably woke up to an alarm clock, turned on a light, and maybe toasted some bread. All of that used electricity. Our modern world runs on it. In our homes, electricity powers our lights, refrigerators, televisions, computers, and washing machines. It keeps us warm in the winter and cool in the summer. In industry, giant factories use massive amounts of electricity to run machines that build cars, make clothes, and process our food. Without electricity, our entire economy would grind to a halt. It's the invisible force behind almost everything we do. The impact of electricity goes far beyond our homes and factories. Look at transportation and communication. Electric trains and subways move millions of people in cities every single day. And now, electric cars are becoming more and more common, which helps reduce air pollution. How are you reading this right now? On a computer or a phone? Those devices run on electricity, and the internet itself is a global network of computers and servers all powered by electricity. It allows us to talk to anyone, anywhere, in an instant. In healthcare, electricity powers life-saving machines like X-ray scanners, heart monitors, and surgical tools. Because electricity is so important, scientists are working on even better ways to make and use it. One of the biggest trends is renewable energy. Instead of burning fossil fuels like coal and gas, which can pollute our planet, we are learning to generate electricity from clean sources. We can use the power of the sun with solar panels, the wind with giant turbines, and the moving water in rivers with hydroelectric dams. These methods create electricity without harming our environment, which is awesome for the future of our planet. We're also making our electrical system smarter. A smart grid is an electrical network that uses computer technology to be more efficient. It can help reduce power outages and manage energy use better, saving energy and money. Combined with the rise of electric vehicles and more efficient batteries, the future of electricity is incredibly exciting. From a spark of static on a piece of amber to a worldwide network that powers our entire civilization, the story of electricity shows us the amazing power of human curiosity and science. It has completely transformed our world, and it will continue to power our future. Consider the following. Science is the key to our future.